In this question, we're now looking at how we can use the integrated rate law to plot a straight line graph of our data. So let's start out by looking at this question. Here we have a fictional scientist carrying out a fictional decomposition reaction of compound AX3, which we can see in our chemical equation here. We're told that the scientist experimentally determines the differential rate law is rate equals K. So our first step is figuring out what is the order of this reaction. Now, if we're told the rate equals K, we don't have any concentration of our reactant in there. So it's like we had our concentration of AX3 here, but it's to the power of 0 because anything to the power of 0 is just 1. So it doesn't need to appear in the equation. So the overall order of reaction for AX3 is 0. It doesn't affect the rate. Now we need to find the integrated rate law for this reaction. So let's head to our reference sheet. We're looking for the integrated rate law for a 0th order reaction. That is here. So this is our integrated rate law for our 0th order reaction. The concentration of the reactant at time t is equal to the concentration of the reactant at time 0 minus KT. So let's select the right equation there. So it's going to be this one here. And again, there's an option with a plus or a minus. I just want to check. Yes, it's a minus KT for the 0th order law. So there's our integrated rate law for this reaction. So now that we know this is the integrated rate law, the scientist wants to be able to plot a straight line graph of this data. So the way we're going to do that is to map this integrated rate law equation onto the equation for a straight line, which is y equals mx plus c. So our y is going to be the concentration of AX3 at time t. So that's a variable that's changing. T is going to be our x variable. So the thing multiplying t, that's going to be our m, our slope. And the other thing is going to be our b, our intercept. So that's how this graph is going to map onto y equals mx plus b. So what should the scientists plot to get a straight line graph? Well, they need to plot AX3 at time t on the y-axis and t on the x-axis. So they're going to be plotting AX3, the concentration of AX3 on the y-axis against t on the x-axis. That's going to get us a straight line graph. Now we're asked what this straight line graph will look like. So we want it to be a straight line. So it's going to be either graph 1 or graph 4, because those, or graph 7, I guess. Those are the ones with straight lines. However, based on our integrated rate law equation, we know that the slope, m, is going to be negative k. So we know that the graph is going to be sloping downwards because k, the rate constant, is positive and it's negative k. So we know it's going to be graph 1 because that's sloping downwards. And the last question there is, what will the slope of this straight line graph represent? Well, we've already said the slope m represents negative k, where k is our rate constant. So if we just draw onto our diagram here, for y, we had the concentration of AX3 at a time t, so at any time. For our x-axis, we had t, and our slope is negative k. So that's when we have a 0th order reaction with our integrated rate law. If we plot our concentration against time on a graph, we can find k by finding the negative of the slope. Let's look at a couple of other examples. In this question, we now have a fictional reaction involving Dg2, which you can see in our chemical equation there. We're told that the scientist experimentally determines the differential rate law is rate equals k concentration of Dg2 squared. So that squared tells us that the rate law is second order for dg2. So the overall order is 2, second order. What is the integrated rate law for this reaction? Let's head to our reference sheet. We're looking for the integrated rate law for a second order reaction, which is here. So here's our rate law. It's 1 over the concentration of A at time t is equal to 1 over the concentration of A at time 0 plus Kt. And remember, A there just represents our reactant. So let's select that equation here. It's 1 over dg2t is equal to 1 over dg2 0 plus Kt. Let's just double check that. Yeah, it's plus Kt for the second order rate law. Awesome. So there's our integrated rate law for this reaction. Now we need to figure out what the scientist is going to plot to get a straight line graph. So again, I want to map this onto y equals mx plus b. So my y is going to be 1 over the concentration of dg2 at time t. So that's a variable. It can happen at any time. Our x variable is going to be the time t. So the thing multiplying our x variable, that's going to be m, our slope. So that's going to be k. And then the plus b, that's going to be this value here, which is 1 over dg2 concentration at time 0. So what should the scientist plot? Y against x. So that's going to be 1 over dg2 against x, which we decided is t. The next question asks, what does this straight line graph look like? So again, it's going to be either graph 1, graph 4, or graph 7, because those are the only ones with straight lines. In this one, we know that the slope is positive k, where k is the rate constant. Since the rate constant is a positive value, we know it must have a positive slope. So that's going to be graph 4. So this one's going to look like graph 4 because it has a positive slope. And our slope there, our m, is just k. It's positive k, where k is the rate constant. So that's going to be our slope of our graph. And let's just write those on here to make that clear. So on the y-axis, we plotted 1 over the concentration of dg2 at all different times. So x was our t. And then the slope we got is k, the rate constant. Okay, one last question. In this last question here, we have a fictional scientist again, a fictional reaction, the decomposition of L2G3, which we can see in our equation there. And in this one, the scientist has measured how L2G3 changes over time, the concentration that is, as the reaction progresses, and they've figured out how to plot a straight line graph of the data. And the thing that they've plotted is ln of the concentration of L2G3 against time. And they got a straight line with a downward slope, so a negative slope. Okay, so let's go to our reference sheet. We're looking for the integrated rate law that involves ln. Here it is, our integrated rate law first order. That's the one that has a ln in it. So let's go and write that down. So the integrated rate law for this reaction is ln, and it had negative Kt. Let's just check that. Yep, it's negative Kt. So that's our integrated rate law for this reaction. So based on that, what does that mean the slope of the straight line graph represents? So again, mapping that to y equals mx plus b. On our y-axis, we've got ln of L2G3. On our x-axis, we've got time. So mapping that to our equation, on the y-axis, we have ln concentration of L2G3. On the x-axis, we've got time. So my slope must be whatever's multiplying x, which is negative k. So negative the rate constant. And that makes sense because our graph shown here is sloping downwards. It's got a negative slope. Awesome. Okay. So now we know that it's this equation that's telling us it's the first order rate law. So that's telling us we know this is a first order reaction. So finally, now we know it's a first order reaction, we can use that to write the differential rate law for this reaction, which is going to be rate is equal to K, the rate constant, multiplied by the concentration of our reactant, which is L2G3, to the power of the order, which is 1. And remember, to the power of 1 is just like saying the thing itself. It doesn't affect it. So we can find that here. So in these questions, we're using our reference sheet. We're choosing the correct rate law based on either what we know from the differential rate law or based on what we have in it. Is it just the concentration? Is it the natural logarithm, ln of the concentration? Or is it 1 over the concentration? And finally, we're using those to map them onto a y equals mx plus b straight line graph to figure out what our slope would represent.